Okay, I see that it's 1 o'clock. So, excuse me. So we're ready for our next talk. Our next talk will be by Sam Fisher, talking about fibering of RFRS groups.
Yeah, thank you. Yeah, the main definition of the talk is what it means for a group to be fibered. So yeah, I'll start with that. So a group G is, sometimes we'll say algebraically fibered to distinguish this from the topological sort of setting where you actually have fibered spaces. So a group is algebraically fibered if and only if there exists an epimorphism. So this is or maybe a surjection of the group to the integers Z. So this is a group homomorphism that is surjective. And we also want the kernel of this homomorphism to be finitely generated. Okay, so it's a straightforward definition. F fibered is a bit more involved. I won't actually give a full definition of this, but what it means is, you want your group to be fibered, but also you want the kernel of the map to be of type F. And okay, well, I haven't really said what this F is, so I'll just put here. F is going to be some what's called a finiteness property of the group. So being finitely generated is a finiteness property. That's sort of the most basic finiteness property. So finitely generated is actually the same thing as what's called type F1. So fibered is the same thing as F1 fibered. Okay. I'll also say F2 is the same thing as finitely presented for groups. So, okay, so there's also this notion of F2 fibered, and then there's a whole sort of world of finiteness properties that are out there for groups. If you know about that, if not, I mean, I'm more than happy to talk about it at some point. Yeah, but okay, that's the main definition of the talk, and we're going to talk about a characterization of fibering for RFRS groups or refers groups. Okay, so the motivation for the definition is manifolds fibering over the circle. So what that means, right, is maybe I should put here somewhere M fibers over S1. So circle, if you can write M as, let's say M is an n-dimensional manifold, M is diffeomorphic or homeomorphic, depending on which category you're working in, to, let's say, what letter should I use? Let me say capital N minus 1 across an interval, and you sort of glue the opposite sides together. So, I mean, the picture is, sorry, this is very small. The picture you have is that M is going to be some manifold across an interval, and then you're going to glue these two sides together. So M is a mapping torus. Okay, and so an exercise is to show that if you have a fiber bundle like this, or if M fibers over a circle S1, and the fiber is compact, then this induces an algebraic fibration of the fundamental group of the manifold. So what you want to do is look at the long exact sequence of higher homotopy groups to show this. So really you just need to show that one of the fibers of the fibration in pi1 injects into the manifold fibering over the circle. Okay, so this is always true for any dimension, and what's really amazing is that for 3 manifolds you can actually go the other way around. So Stallings showed this in 1969. So if you take a compact 3 manifold and the fundamental group algebraically fibers, then actually that algebraic fibration was induced by a topological fibration of the manifold. So you're kind of going the other way around for 3 manifolds, which is really, I think, incredible. And the proof is like very sort of hands-on. It doesn't use any crazy machinery or anything. It kind of just builds the fibration by hand. And I should also say that the sort of same kind of thing works for manifolds of dimension n greater than or equal to 6. So this was studied by Farrell in his thesis. So there are conditions now. It's a lot more complicated. There are conditions for when you take an algebraic fibration of the fundamental group of an n manifold. When is that actually induced by a topological fibration of the manifold over the circle? Okay. Yeah, the reason it works for dimensions n greater than 6 is because it relies on surgery theory, and that those techniques only really work for high dimensions. Okay. Yeah, so that's sort of the manifold topology side of the motivation. I'm more in group theory, I would say. So for me, what's nice about an algebraic fibration of a group is that it gives you a way of writing your group as a semi-direct product with Z, where this kernel here is going to be finitely generated. Yeah, this is good because often, I mean, you want to show something about your group, and if you know that it fibers, you can write it as a semi-direct product, and then hopefully somehow the complexity of K has decreased, and you can reapply the argument to K and hope to use some type of induction. And I'll show an example of that type of argument at the end of the talk. Okay, and now, so RFRS groups. This is, I said it was fibering of RFRS groups. So RFRS stands for residually finite rationally solvable, pronounced RFRS. So the residually finite part, maybe some of you will be familiar with. So a group is residually finite if you have a chain of finite index subgroups. So this little Fi that I've written on top of each inclusion here. So you have a chain of finite index normal subgroups such that the intersection of the chain is the trivial group. So this is what it means for the chain to be residual, and it intersects at the identity. And then the other condition is a bit more complicated. So you want the kernel of this free abelianization map. So this is free abelianization. So by definition, the free abelianization of a group is just you abelianize it and you mod out by the torsion. Okay, so you want this kernel to be contained in the next group of the residual chain. So this is a kind of awkward and technical definition, but it sort of makes a lot of this stuff work. It was introduced by Agel in his 2008 paper on virtual fibering of three manifolds. So he showed that if you have a three manifold and the fundamental group is RFRS, and the Euler characteristic is 0, then your manifold is virtually fibered. So that was a sort of a big step in the resolution of the virtual fibering conjecture. Okay, some facts about RFRS groups. So right-angled Artin groups are RFRS. So rags are RFRS. This is the motto. Yeah, if you have some nice combination theorems. So if G and H are RFRS, then the product is RFRS. This is easy. This is just an exercise. You just take the two residual chains and you take the product, and those will be that will form a RFRS chain for G times H. The free product is also RFRS. Okay, this uses some Bass-Serre theory. This it's in Agel's paper. It's quite involved, I would say, though. Okay, RFRS passes to subgroups. That's the next property here. If you have a group that's RFRS and a subgroup, then H is also RFRS. So now we have that all subgroups of rags are RFRS. And that's all of a sudden a pretty large class of groups. There are lots of, there are all kinds of subgroups of rags. Okay, and then more examples. Surface groups are RFRS. Right-angled Coxeter groups, for those of you who know those, are also virtually RFRS. And so also in the last talk, special cube complexes were mentioned. The fundamental group of those are virtually RFRS. Okay. Okay. Yeah, that's I think all I'll say for the RFRS condition. Okay, so the characterization I'm going to give of fibering of RFRS groups is going to involve L2 Betti numbers. These have a very technical definition that I just don't have the time to give in a short talk like this. So I'm just going to list off some properties about them. So the L2 Betti numbers of a group, it's a sequence of numbers. So you have a group G, you assign this BP to G. P is just any natural number, including 0, and they're going to be positive real numbers. So it's just a sequence of numbers you assign to your group, and they have the following nice properties, which make them a good invariant of a group, I would say. So the first is that if you take a finite index subgroup of your group G, then the L2 Betti numbers scale. So they scale with the index of the finite index subgroup, which is already quite nice property that makes this alone makes L2 Betti numbers a very nice invariant for groups. The 0th L2 Betti number of a group is 1 over the order of the group, where I'm taking this quantity to be 0 if it's an infinite group. So also, this shows that the L2 Betti numbers don't need to be integers. Like the Betti numbers of a topological space, those are integers. This is not how it works for L2 Betti numbers of a group. Okay, so if G is of type F, okay, so this is one of the finiteness properties that sort of goes into the finiteness properties I was talking about earlier. What this means is that, I wrote it there actually. So the group G has a finite classifying space. So KG1 is a classifying space that means that the fundamental group of this topological space, we can call it X, is G, and the universal cover is contractible. Okay. And what it means for it to be finite is it means that it's a cell complex with finitely many cells. So okay, if G is a group of type F, we can define the Betti numbers of the group by just looking at the Betti numbers of the space. So, and then using that, you can also define the Euler characteristic of the group. So we're using here that the classifying space is a homotopy invariant too, for all this to work. So the Euler characteristic of the group is the alternating sum of the Betti numbers, the usual Betti numbers of this classifying space, but it's also the alternating sum of the L2 Betti numbers of the group. So even though the L2 Betti numbers in general differ from the usual Betti numbers, they do have this relationship. Okay, and here's something that you can actually take as the definition of L2 Betti numbers for residually finite groups of type F again. So this is called Luke's approximation theorem, and it says that the pth L2 Betti number of G is the limit as n goes to infinity of the usual L2 Betti numbers of Gn. I'll say what Gn is a bit in a second. Okay, where this is some residual chain. So this is why we need the condition residually finite to have access to a chain like this. Okay, so this can be used as the definition of L2 Betti numbers. So just using the usual Betti numbers of the finite index subgroups. And lastly, the L2 Betti numbers vanish if for all P if G is an amenable group. Okay. Okay. So recently, David Kielak proved this nice characterization of fibering for virtually RFRS groups. Virtually meaning it has G has a finite index subgroup that is RFRS. So yeah, the statement is if G is finitely generated and virtually RFRS, then G virtually fibres, meaning there exists H of finite index in G such that there exists, H fibres. Okay, so this happens if and only if the first L2 Betti number vanishes. So using Stallings' theorem for fibering of 3 manifolds, this actually generalizes Egel's theorem about fibering of manifolds with RFRS fundamental groups. So this gives a completely algebraic characterization of when, well, obviously of when a group fibers, but also tells you when a manifold fiber is using this Stallings theorem, telling you that if the fundamental group of the three manifold fibers, then also the manifold itself should fiber over the circle. And the results I wanted to present today is a generalization of this. So now if we take G to be of type FPN over the rationals, so this is a new finiteness property, but I should just say that FP1 over the rationals is equivalent to finite generation. So again, I've highlighted in blue the parts that generalize Kehlach's theorem. So if you're of type FPN over Q, that's a generalization of finitely generated. Your virtually refers now G virtually FPN over Q fibers, if and only if the first P L2 Betti numbers of the group vanish. So these in general, these FPN over Q are going to be stronger finiteness properties than finite generation. They're kind of a algebraic analog of having a classifying space with finite and skeleton. That's one way to think about them. Okay, and to finish with the time I have left, I just want to give a couple of applications of this result. So there's this general question about amenable groups of asking when is an amenable group elementary amenable. So here we can sort of answer that under these maybe strong conditions. But if you take a group G that's amenable, refers and of type FP over Q, so that is this just means FP n over Q for all n. It's implied by type F. So type F implies type FPQ. So if you're a group with a classifying space with a finite n skeleton, with a finite classifying space, then you're of type FP over the rationals. Okay, so then G is polycyclic by finite. I don't have time to define polycyclic by finite, but it is a special subclass of elementary amenable groups. Again, for those of you who know what elementary amenable groups are. Okay, so a sketch of this. So if G is amenable, that means that G is L2 acyclic, meaning, yeah, that is one of the properties I said earlier. All of these L2 Betti numbers vanish. That means that G virtually fibers. I can then write G as a semi-direct product of n with Z. That's what it means for it to fiber. This is up to finite index. Okay, once we have this, theorem of Feldman tells us that the dimension of the group n drops. So the CD is cohomological dimension. I'm not going to say what that is. Again, n is an amenable group because it's a subgroup of an amenable group. So it also virtually fibers, and then we reapply this argument until the cohomological dimension is 0, which means you've landed at the trivial group, and you conclude that the whole group must have been polycyclic by finite. So what you're doing really is you're writing, okay, G up to, let's say, finite index is going to be something like N1 semi-direct Z, and you keep doing this semi-direct Z, and you keep splitting the group as a semi-direct product with Z. And that's kind of what it means for the group to be polycyclic by finite. You get this decomposition. Okay, and then finally, to finish, I just want to talk about this conjecture of Baer, which states that if the group ring ZG is Noetherian, then G is polycyclic by finite. So it's known that if your group is polycyclic by finite, then ZG is Noetherian. So we can answer this in the case where G is virtually refers type FP over Q. So if the group ring is Noetherian, that means that ZG is what's called an aura domain. This just means that you can localize this ring. So even though it's a non-commutative ring, you can still localize it. That's all aura means. Kehlach showed that if you have an aura domain, if your group ring is an aura domain, then your group G is amenable. You finally use the theorem we just showed to conclude that G is polycyclic by finite. So this confirms this Baer conjecture in the case when G's refers and of type FP over the rationals. And yeah, that's all I wanted to say.
Okay, let's thank Sam. And I have a question to start. But back at the beginning of the talk, when you were motivating fiber, you talked about the topological results by Stallings and in higher dimensions, was it Farrell?
Yeah.
Yeah, Farrell. So in this more refined context that you've been looking at, is there a way that you can reframe or apply some of these things, your end results back towards these kinds of topological results, or there's specific topological settings that motivate looking at these particular groups?
Yeah, so recently Bruno Martelli and two of his students showed that there exists a hyperbolic 5 manifold that fibers over the circle. So I've been trying to apply this. So they also construct a 7 manifold, hyperbolic 7 manifold that has a fundamental group that algebraically fibers with finitely presented kernel. So so using this, you can actually upgrade that to find a hyperbolic 7 manifold that fibers with finally presented kernel and type FP over the rationals. And I mean, the hope is that you could use then these things that Farrell did to promote this algebraic fibration that has really good finiteness properties to an actual topological fibration of the manifold and get an example of a 7 manifold fibering over the circle. So that would be, I guess, more of a potential, a potential application to topology.
Is the idea that then, the fibers would have to have certain kinds of properties on their fundamental groups? Yeah,
so if you could promote FP over the rationals to FP over the integers, I know I haven't said what any of these things are, but then you could say that the fiber is actually like a finite CW complex, and then you can, I think then things would work, but I don't really have any way to go from rationals to integers right now. So yeah.
Any other questions? All right, well, if not, let's thank Sam again. And our next talk will be in about 8 minutes. It's Sergey Melikov. Oh, Katerina, did you have a question?
So sorry, no, I wanted to clap and I raised my hand. Excuse me, but it was a nice talk. Thank you.
No problem.